Okay, I wanted to start us off with the second part of the 7.4 notes. And we're going to start with the side splitter theorem, which is a very convenient theorem that we can use to set up a proportion in similar triangles. So if we have this figure where there are parallel lines there, what we can show is that this side in a ratio with this one, it's the same ratio as this to this. So for example, if this was 3 and 6, then this, and maybe this was 4 and 8, 3 over 6 is 4 over 8. That's what this is getting at. Pretty neat, but we don't really have an immediate reason why that's true, so we gotta maybe sketch a proof of it. So if we do have this picture, and if those lines are parallel, that means that corresponding angles are congruent. So what does that mean? It means that this angle and this angle are congruent. And also this angle and this angle are congruent too. So these triangles, and I'll redraw them below, are similar by angle-angle similarity. We just showed that, right? And hopefully you see that these are corresponding angles, right? That's a mini picture right here that you can look at. That's corresponding, and they're parallels, so they're congruent. So here's what RQS looks like, and here's the bigger triangle, which is what XQY looks like. All right, and those are they're similar because they've got matching angles here and here. And also Q is Q, so we really have 3 angles that match. So these are similar triangles. So because we have similar triangles, we can set up a proportion that says that Q, or XQ, so this length, switch colors, this length to this length, so that kind of, it's the scale factor, right? It's the larger result divided by where it came from. That should be equal to doing this on the other side. YQ to SQ. They should have the same scale factor, and that's what I'm writing here. But we know based on this picture that XQ is no different than XR plus RQ over RQ, right? Segment addition says that this plus this is XQ, and YQ can be broken apart into 2 segments, YS and SQ. And then we have a lot of simplifying that can happen here, because when you add, this is actually a combined fraction. You can split it up into this. And the same thing over here. But the really cool thing about this theorem is that these 2 things, since they're a ratio of itself divided by itself, these are both equal to just 1, because when you divide something by itself, you get 1. So there's a plus 1 on both sides. So we can subtract 1 from both sides, and we get our result. Again, what is this telling us? I would advise you to just look here. It's saying, hey, if you had this diagram, then 3 over 6 is equal to 4 over 8. And it's just a result of similar triangles and a little bit of clever algebra. So let's practice with these. So how would you set up side splitter? Well, you circle the side, you split it, and then you write down the resulting fraction. So 18 over x is 21 over 14. And you can check with what was written above. It obeys the formula. Yeah, it could be like flipped upside down. If you, this is the same as this. because if you cross multiply, you get the same thing. So the order doesn't really matter. Like if you do 18 over x or x over 18, it's got to be consistent. Notice I'm taking this bigger length divided by a smaller one, this bigger length divided by a smaller one. And then you just have to cross multiply, and we get this, and then x is just 12. You could do it here too. You just circle the side and split it. So 8 over 10 is 6 over x. So we get that x is 7.5. And again, circle aside, split it. So 12 over x plus 1 is 9 over x. Cross multiply. Distribute. Get the x's together by subtracting. And you'll eventually get that x is 3. Okay? So kind of nice and easy, but we have to kind of respect the proof of why this is true. We're not really setting similar sides equal to each other. We're setting parts of similar sides equal. So this is called the side splitter theorem. And the last thing I wanted to talk about briefly is just the midsegment. It connects the two midpoints. Of two sides of a triangle. And the resulting triangle is actually going to be similar by SAS similarity. How? Well, again, imagine if this was like 5 and this was 4. If D is a midpoint, this is 5 and this is 4. So if we're talking about the big triangle and the little one, so this one here has sides of 4 and 5, whereas the big one has sides of 10 and 8, right? Well, this angle is included on both triangles, right? So this is a perfect case where we see that this side here is similar but not equal to, they're proportional, right? I'll put these little like sideways tick marks. Basically, the scale factor between both sides is 2, and they have an angle in between that's equal, so this is perfect SAS similarity. Some cool things, though, about the midsegment is that those two connectors between the two midpoints here and here, kind of like the horizontally kind of ones, are parallel by the it's actually by the converse of the corresponding angle theorem. So if these triangles are similar by SAS similarity, I know that all these angles match up, right? And if we have a picture like this, and those angles are equal, then the lines are parallel. And that's by the converse, the opposite of the corresponding angle theorem. So those are parallel when you have a midsegment. And the real takeaway, midsegment, mid normally means half. So the midsegment is half the length of the side parallel to it. So if this was, let's say it's, 6, then AD is 12. It's the midsegment's half the length of the parallel side. Cool. So how can we use this? It says solve for x and then solve for UV. So I know this is a midsegment because it's connected. It's connecting the midpoints of both sides. So I know right away that this is 5. Okay, and triangles with the midsegment drawn, they have parallel lines. So I know that this is my scenario here where I have 65 and x. So it's pretty clear that x needs to be 65 degrees because it's corresponding with a 65-degree angle. Okay, so kind of a menacing picture, but not really. The mid-segment stuff isn't too bad, you guys. Okay, so it says set up a proportion to solve. Okay, so if I draw my separate triangles, right? You could set up a proportion between this side and this side. So how about 12 over 6 is x over 5? So x is 10. So you could do something like that. Or you could notice, hey, this is a scale factor of 2, so I better double this. Or you could say, hey, 5 is a midpoint. I'm sorry. 5 is the length of the midsegment because these two lengths are equal. So, and a midsegment is half of the length of its parallel side, so this is 10. So 3 different ways why that can be 10. But if you were told that 5 is a midsegment, you can say x right away is just 10. It's just double. And it's double because that's the scale factor between the picture. Okay, and I wanted to comment real quickly on this sketch. It says the Triforce symbol is from The Legend of Zelda, and it's formed with 4 equilateral triangles. Well, there's really 5. There's 1, 2, 3, 4, and then there's a big one, right? It says if AB is 10, what is the length of this? Okay. Well, we could try and use the midsegment, in which case we would kind of ignore these for a little bit. But is that really the midsegment? Well, equilateral triangles all have the same sides if they're all stacked up like that. So that guarantees that y and z are midpoints of their sides. So this is a midsegment. So this has to be 5. Okay, so yz is 5. In fact, all of the lengths of these triangles are 5. And then it says name 2 triangles that are similar but not congruent. So we could look at the big triangle, which is 10, 10, and 10. It's equilateral as well. And then we could look at the one in the middle, which is 5, 5, 5, upside down, x, y, z. Those would be similar because they're all 60 degrees, right? So the angles are all the same, and the sides are all in proportion because to go from the larger one to the smaller one, you always multiply by half. And that's a common theme with the midsegment. So yeah, I would say that triangle ABC is similar to XYZ, but not congruent because they are not the same size at all. Okay? Cool. So finish up the rest of those homeworks and let me know if you have any questions.